Hi everyone, in this video I'm going to discuss about a vertical cantilever beam like a wind turbine which is pushed down by gravity and rotor and nacelle loads. This downward force along the center line of the vertical cantilever beam is called axial force that I'm going to explore in this video. Imagine a tall tower fixed at the seabed or soil called the vertical coordinate z, measured from the base z equals 0 up to z equal L, which L is the length of this vertical cantilever beam. Now, even if there is no wind and bending, the tower still carries load. The nacelle and rotor at top of tower have weight. The tower itself has weight. All of that weight stacks up toward bottom. We call this internal vertical force the axial force PZ. At the very top, PZ is mostly just mass of the nacelle rotor. Lower down, PZ is a large value because it has to support everything above. However, near the base, PZ is the largest. So if I plot its typical vertical distribution, axial force magnitude on horizontal axis and Z on vertical axis, PZ magnitude generally increases as we move down toward the base, as shown by this red curve. When the tower is perfectly straight, this force is purely vertical. There is no sideways effect from PZ yet. Now, imagine the wind pushes the tower so it deflects sideways a little. Let UZ be the sideways displacement of the tower at a given height Z. So instead of being perfectly vertical, the tower center line is now slightly curved, which represented mathematically by UZ. At any given height Z, that bent shape has a small tilt angle from the vertical axis. For better clarity, I selected a segment of a small tilt angle and exaggerate it in this cartoon. Let's call that angle theta. This is basically how much the tower is leaning at that point. Geometrically, the slope of the deflection is given by this formula. For a small bending, the tilt angle theta is about equal to that slope as given by this formula. If the slope is 0, that part of the tower is still vertical. If the slope is not 0 at given z, as shown here, that section is tilted. In this final slide, I'm going to focus on what happens to the axial force when the tower is subjected to a small tilt. At a given height, z, we have axial force, pz, downward before tilt. After a small tilt of theta, this force is along the tilted center line of the beam and is no longer vertical downward. Let's zoom in and show this small vertical segment by this cartoon. It's now clear that the tilted axial force at any given height z can be split into two components, as shown here: a vertical part and a horizontal sideways component. From basic trigonometry on a small angle theta, vertical part is equal pz multiplied cosine theta, and horizontal part is approximated by pz multiplied sine theta. For a small angle tilt, we know that sine theta can be approximated by theta. So the sideways component is then shown by this formula. P side is approximated by multiplication of axial force and tilt angle theta. From previous slide, we got the relationship between the theta and the slope by this equation. If now we put these two equations together, we get our objective for this video as shown by this equation, in which the horizontal part of the axial force is related to the multiplication of axial force by the derivative of the displacement at any given height. I should emphasize that the sideways component is not just a detail. It actively pushes the tower further sideways. So even if the original wind load was what started the bending, the axial force itself is now helping to bend the tower more, or at least it can modulate the load-induced bending. This is why tall, slender towers under heavy load can become easier to bend. I will discuss contribution of this axial load in modeling of vertical cantilever beam using Euler-Bernoulli equation in another video.